Hello, class. This will be a recorded lecture for section 5.6. This is the last of the sections in chapter 5. And what we're going to do is tie in the idea of the zeros and them possibly being complex and show you how to do those calculations. And so I'm going to introduce a theorem that we don't use very much, but it's quite interesting since we're in an algebra class. And it's called the fundamental theorem of algebra. And basically what it says is that if you have a polynomial with a degree of at least one, so a linear equation or more, that it has at least one zero, and it's in the complex plane. And so a couple of things to remember. One is that in the complex plane, real numbers are a subset. So if it's a real, it's also complex because you can always write it. For example, I have up here a real number for the number 4 could be written as 4 plus 0 I. So it's always a subset. And here's how the polynomials can be written. An minus x times each one of these zeros all the way down to the constant term, excuse me, couldn't think of that word, all the way down to the constant term. And so what's kind of interesting is this corollary, actually. What a corollary is a small theorem, but this one's much more useful. The fundamental theorem of algebra doesn't show you or tell you how to do any of the calculations, but this one's kind of nice, and this comes from Descartes' theorem, where since complex conjugate zeros occur in pairs, that if you have an odd degree, remember that if you add even numbers together, they always end up being even. You have to have at least one real zero. And that's because complex conjugate or complex zeros occur in pairs and they end up being conjugates of one another. And that's because of the quadratic formula. And so I'll show you that in a minute, but I do want to introduce this last thing. And this is the idea of what I just said, that non-zeros or non-real zeros, which are complex zeros, occur in pairs and they occur as conjugates. And so if we take a look at the quadratic formula, I'll kind of give you a quick example of why. So this is minus b plus or minus the square root of b squared minus 4ac all over 2a. So you could see that, for example, if we ended up with something that looked like this, minus 5 plus or minus the square root of minus 4. So when you calculate that, that's going to be minus 5 plus or minus 2i. So you could see this plus or minus. This is the only place where we could get a complex number, right? And when we do that, it always has to be a plus or minus of that complex number. And the I only occurs there because of the square root. And so you see it always occurs in pairs. So for example, if I gave you a problem like this, where you have degree of, say, 5, and we had these zeros. You had 1, you had 2i, and you had 3 minus I. And I said, what are the other zeros? Well, you look at the complex and you say, okay, there are no conjugates of that in there, so you have to have the conjugate. So what's the conjugate of this? That would be minus 2i. And what's the conjugate of this? It would be 3 plus I. So how do you write that out using the fundamental theorem of algebra? Well, remember we had this an, and now you have to subtract, right, all of these zeros. And so you're used to this one. If it's a real one, you just subtract it. So when you plug 1 in, you get 0. But these are a little bit tricky. And so basically that would be minus 2i, right? And this would be x minus a minus 2i. So that turns into a plus. And then this would be x minus 3 minus I. and x minus 3 plus I. So I would recommend when you see these complex numbers, put them in the parentheses like that. Even here, you could see that we could simplify this now, right? And it would just turn into x plus 2I. But when you have both a real and imaginary part, it's kind of tricky to do it that way. Last thing I want to point out is that when you multiply this all out, which is quite tedious, if you don't do it this way, it's going to be 1,000 times more tedious, is that always multiply the complex conjugate factors together first. Because why complex conjugates are nice when we multiply together? The imaginary part goes away. So as a review, I'm just going to do this part right here. So let's multiply that all out and see what happens. Because you would do this first, then this one second, and then you could just keep multiplying after that. But let's do this one first. So x times x is x squared. So this would be minus 3, or x times minus 3, which is minus 3x. And this would be x times, these are two negatives, so that would be plus xi. So let's do this minus 3. Minus 3 times x is minus 3x. Minus 3 times minus 3 would be plus 9. And then minus 3, and that would be plus I. So that would be minus 3i. And so the last one would be I times x. So that would be, or excuse me, minus I. I almost forgot my minus. See, minus I times x, which would be minus xi. And then minus I times minus 3, which is plus 3i. And then minus I times plus I is minus I squared. And remember, what does minus or I squared equal? Minus 1. So this would end up being plus 1 as a conversion. So you could see that all the i's better cancel or I did something wrong. So this here, it would cancel with this one here. So that's good. And then 3i and minus 3i cancel. And so that's good. And so now we put like terms together. So there's only one x squared. So it looks like we have minus 3 and minus 3 is minus 6x. And then we have 9 and 1, and that would be plus 10. And so now that would be the multiplication of this one. And so you would do this one next. That one's a little bit easier. And then you would have to multiply all that through. So that ends the first of the two. I think there's going to be 2 recorded lectures for section 5-6. The next one, we're going to go through an example of a polynomial that does have complex zeros and show you how to calculate.